Welcome back to Young Engineers of Today. I hope you're ready to continue with Arduino. This is actually going to be our last lesson for Arduino before you guys have the competition. So uh, there you go. You got that to look forward to. We're going to get through servos pretty quickly, and we're going to spend some time on transistors. I do have one sample question to go over with you guys. We'll spend some time discussing, reasoning behind it and everything like that. If it's anything like the middle school, it's going to be a multiple choice, so you got that going for you, which is nice. And then we will leave it open to general question and answer time. Now, we might run the full hour. In fact, chances are we're probably going to run the full hour. We might not. If that happens, though, that's fine. We'll just, if we go through everything and you guys don't have any further questions, we'll just go ahead and end it a little bit early. But we'll go through everything as best we can. I might go through servos a little quickly, but I want to make sure that I get to transistors at least. So we'll spend a decent amount of time on transistors. But actually, let's go ahead and start with the sample question so that I can at least make sure that you guys see it before we continue. Okay. Sorry, it's going to take me a moment to get it open, just because it doesn't want to cooperate. Oh, okay. We don't actually have the multiple choice at the end. That's fine. So this right here is the sample question. It just says, ideally the LED is supposed to blink once a second. Currently the LED does not blink, nor does it even light up. Inspect the hardware and software for problems and solutions. Answer multiple choice questions. In this case, you would get a set of choices that would provide possible answers for what it could be. Fair warning, there are all of the above and none of the above answers. So I always hated those. I just thought you guys wouldn't want to be blindsided by those. But yeah, so the LED does not blink at all. And we're not sure whether or not it's a hardware or a software problem. So let's go ahead and take a look at the hardware. So as you can see, you've got the LED hooked up to pin 10 on the Arduino. It's got a resistor hooked up to it, and it's hooked up to ground. Does anything look odd about this at all? I'll give you some time to think about it. Pin 10 is hooked up to the plus on the LED. The minus is hooked up to the resistor. So it's hooked up to the anode. Pin 10 is hooked up to the anode, and the resistor is hooked up to the cathode. And then we'll take a look at the code. So you've got a variable holding the LED. You've got your pin mode, and you've got digital write. So the LED turns on, delays for a single millisecond, and then off for 1 second. So here, this is actually, since all this bit is commenting up here, I'm actually going to scroll it down this far so you can see sort of both the hardware and the software at the same time. So potential issues. What might be preventing this LED from turning on? Spend some time thinking about it. If you have an idea as to what the answer might be, go ahead and throw it into the question box. All right, yeah, there you go, Edwin. That's definitely probably the biggest one. What else might be causing a problem? Yeah, you got it, Arden. Yeah, you guys are definitely identifying that problem in line 6 of the code. The LED is hooked up to pin 10. However, the LED variable, the LED pin variable in the code is set up to be pin 12, which is a bit of a problem. That does prevent power being sent to the LED. So that's definitely the reason why it's not turning on at all. However, you might be running into very vague issues, even if you got that set up correctly. What else might be weird about this? Yeah, yeah, definitely, Edwin. That's another one. The fact that it's set to be on for a single millisecond could mean that it is difficult to see. Like it might blink so fast that you might actually miss it. Now, again, this is going to be multiple choice. So if one of the answers is going to be the fact that there's a problem on line 6, and another one of the answers is going to be that there's a problem on line 14, and you're only allowed to pick one of them, you would definitely pick the line 6 one, because that is definitely preventing the LED from turning on. If there are multiple answers, you might also want to mention that, line 14 here is going to make it difficult for the user to be able to see the LED lighting up. You might want to make the delay longer so that the LED stays lit for longer, like even 10 milliseconds, that kind of thing. Um, so yeah, that all depends upon what the answer, like what the possible answers might be. But definitely, the biggest issue with this right now is the fact that in line 6 of the code, it's set up to light up the LED through pin 12, and on the hardware, it's set up to light up the LED through pin 10. That is, I mean, that's the root of the problem right there, the root of the problem, the LED not turning on. You got a couple of things you can do. Either you can change the code so it's set up for pin 10, or you can unplug it from pin 10 and plug it into pin 12. Do one or the other, obviously. Don't do both, because then you're just switching them around. But one of those would be able to make the LED light up at least, even if it's for only a single millisecond. But yeah, this is an example of uh, the problems that you'll see during the Amazing Mechatronics competition. So this is actually pretty simple, right? I mean, this is question 1, but that doesn't mean that it's going to suddenly become just like wildly complex. Like if you've been attending the classes or at least watching the videos, if you've been taking notes and stuff like that, you should have all the tools you need in order to be able to answer these questions. Definitely. Um, and certainly one of the biggest tools that you're going to have is going to be able to walk through these problems and spend some time at least talking yourself through it and figuring out all the possible solutions and what they could potentially be. But yeah, so let's actually spend some more time working with servos, and then we'll work with transistors, and then if we have, I'll stop at 8:50 anyway, so that we have some time to do question and answer and everything like that. But if we have additional time, like if we end up ending at 8:40 or something like that, well, we'll leave it open for question and answer at that point. You guys can ask all the questions you've got. Otherwise, at that point, you're more than welcome to head out. But let's go ahead and get started. So we've been working on servos, and we actually got the servo hooked up to the Arduino. There we go. We got the servo hooked up to the Arduino, but we didn't actually finish the programming side yet. So let's go ahead and let's pull up our circuit again in circuits.io, or pull it out of a box if you're working on it physically. Give everything a minute to load up. All right, we're actually going to forget the potentiometer for right now. Boop, gone. We've got our servo plugged in to the power and the ground, and then the middle one, the white circuit, is hooked up to pin 9 on the Arduino because that's our signal, right? Remember, it takes a servo takes a timed pulse and translates it into a specific rotation. So it might rotate 60 degrees or 90 degrees or 100 degrees or 12 degrees, whatever. It will rotate a certain amount. And that is how it takes, that is how it functions, essentially. It takes a timed pulse and turns it into a rotation of a specific amount. And that's the important thing, is a specific amount. It's different from a regular motor in the sense that it doesn't just spin continuously. And if you provide it with more power, it'll spin more and faster. It will not spin unless explicitly told to, and even then it will only spin a certain amount. It will not spin forever. It's meant to rotate itself to specific positions and be more of a fine control motor than a wheel for a car or something like that. So let me go ahead and pull up the Arduino code again. So I'm starting over from scratch just so we can spend some time reviewing the code as well. Who remembers what this was? This right here. Okay, so that allows you to use that command, definitely, but there was a name I used for it. Does anybody remember what that name happens to be? Yeah, library, exactly. That's the one. It's a library. It's just a collection of pages of code that include instructions on how to manipulate a servo and how the Arduino could talk to a servo and stuff like that. And by using this pound include, or hashtag include, whatever, technically it's called an octothorpe. By using this pound include servo.h, we're actually telling the Arduino code to include all of those pages of code that have instructions on how to operate a servo. Then we expand upon basically this allows us to expand upon our code. We introduce additional commands that we can use, including, whoops, good Lord, there we go, the ability to simulate a servo in our code. Now, when I say simulate, I'm not talking about this intense 3D model of a servo or anything like that. I'm literally just talking about a set of numbers and variables that represents a servo in the code. This is about as simple an abstraction as you can get. All it does is it just stores information about the servo, like its current position, maybe even its last position, what position it should be at, things like that. It's a very simplistic representation of a servo. It's basically just containing information about the servo. But we need that in order to be able to communicate with it. So in programming parlance, we've essentially instantiated a servo object called myServo. In terms of stuff that you're familiar with, think of this as a specialized kind of variable that we can do additional stuff with, and we've named it myServo. So we could have called it, chicken pad thai, because I'm hungry. We could have called it Mr. Magoo. We could have called it Tom Selleck. We could have called it whatever we wanted to, but we called it myServo because that is at least mildly useful. We know it's a servo, we know it's ours, and it's just a nice placeholder name. We could have called it I don't know, leg or knee servo, and we could have had left, and we could have had knee servo right, and elbow servo and stuff like that if we were building like a robot that had servos on all its joints and stuff. But we're not, so we're just going to give it the nice placeholder name, my servo. But this name could be whatever you want it to be. We just reference it later. So now we're initiating the let's go as fancy as possible. We're initiating the attach protocol on the Arduino. Essentially, we're telling the Arduino that there is a servo attached to pin 9. Specifically, this servo that we've hooked up. We've called it my servo in the code. If we had multiple servos, we could have different names, but this one is called my servo. And we've told the Arduino that my servo is hooked up to pin 9. That's all the attach is it just tells the Arduino that it's hooked up to that pin. Then we could say my servo dot write. Now this is position. We actually need to create a variable called position because otherwise it's going to freak out. But this is the write command for that servo. And now what we're telling the servo is to spin to a specific position. What is this position? Well, let's go ahead and instantiate that variable. So we're going to create an integer variable called position, POS, short for position, and set it equal to 0. So now we've got an integer variable. It's called position. It's equal to 0. That should be stuff you guys are pretty familiar with at this point. So when we write to my servo down here, we're telling it to go to position 0, right? Because that's the value that's stored in position. Now we could, if we wanted to, we could say my servo dot write 90, and it would tell it to go to position 90. This is in degrees. So what we're saying here is rotate to 0 degrees, essentially the start position, and then turn 90 degrees. We could say my servo dot write 180, and it would turn 180 degrees and stuff like that. So you get the idea. So let's go ahead and delete those. And let's make it so that the servo actually changes position. So what we're going to do is we're going to get it started out so it turns to position 0 before it starts to turn. So we're going to say for, and these are the for loops that we did a few lessons ago. So we're repeating bits of code. However, we're leveraging the fact that we're going to be excuse me, good Lord, using a variable to keep track of this. So we're going to say for position equals 0, position is less than 180, and position plus plus. So what's exactly happening here? Well, position is equal to 0. Even if position wasn't 0, as soon as we start this for loop, position will start at 0. It will just, whatever value was in position will be thrown out and will be replaced with 0. Then the loop will run as long as position is less than 180. Then every time the loop runs, we're going to add 1 to position. And all we're going to say is my servo dot write position and then delay 20 milliseconds. So now we're going to write that position to my servo, and we're going to wait 20 milliseconds, and then we're going to run through the loop again. And it's going to do this for position from 0 to 179. We don't want to go the full 180 degrees, but we want to at least get right up to it, because here we're going to set position equal to 180. So remember, as soon as this for loop is done running, as soon as we hit 179, as soon as we hit 180, actually, this is no longer true, right? So it gets dumped out of this for loop into this one. So we're going to set position equal to 180, and we're going to say as long as position is greater than or equal to, well, let's say as long as position is greater than 0, and then position minus minus, which is the same thing as position plus plus, except we're just subtracting 1 from position each time. Then we're going to say my servo dot write position delay 20. So based on all of that, what do you think this code is going to do? Okay, so it's going to move the servo 180 degrees, then back again after 20 milliseconds. Where is that 20 milliseconds pause going to be? 20 millisecond pause going to be? At 180 degrees and at 0 degrees. Okay, okay. Do we have any dissenting voices in that? Does everybody think that's what's going to happen? At the 20 millisecond delay. Okay. Well, sorry, could you expand upon that? What exactly do you mean? Okay, so you're saying after it's turned however many degrees. Ah, yeah. So there you go. Yes, it's definitely going to turn 180 degrees and then back to 0. That will certainly happen. However, that 20 millisecond delay actually happens each time it turns 1 degree. Because you see, it's inside of the loop. So each time this runs, when position is 0, it's going to write position 0, and it's going to delay 20 milliseconds. Then position is going to be 1. Then it's going to write position 1, then it's going to delay 20 milliseconds. Then position 2, write 2, delay 20 milliseconds, so on and so forth. And it's going to do this until it hits 180. And then it's going to come down here, it's going to write 180, and then it's going to delay 20 milliseconds. And then it's going to write 179, and it's going to delay 20 milliseconds, and blah, 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 blah. So actually, it will wait 20 milliseconds after each time it turns 1 degree. So that is the rub. This is, by doing this, we're actually we're throttling how quickly that servo will turn, which is something we kind of need to do. But yeah, so that's our plan. So let's go ahead and dump this code into our Arduino. Boop, copy and paste into the code editor, or upload to your Arduino for those of you running a physical Arduino. Upload and run, and let's watch the servo. And hey, look, there it goes. Spin, 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 turn 180, go back. Spin, 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 turn to 0, go back. Spin, 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 turn to 180, go back. And all it's going to do is just going to go back and forth to 0, to 180, to 0, to 180, back and forth. Thanks to our for loops here. If we wanted to make it run a little bit faster, we could decrease the delay, and we'll actually notice the servo will spin twice as fast in this situation. If we do this, there it goes. Now it's going twice as fast because it's only delaying 10 milliseconds in between each 1 degree increment. So now it's turning faster. If we did 1, the servo would be turning ridiculously fast. So we put the delay in there so that it actually spins at a sane speed. Servos are not necessarily terribly fast things, and so we don't necessarily want to have it spin that quickly. So we introduce the delay so it doesn't start flopping around like a fish out of water, and we don't potentially burn out the motor, because depending upon the servo, that is a thing that you could accidentally do. And then it won't turn at all, and then it'll just be a boring old thing. So we introduce the delay so that we have it has some time between each time it turns for multiple reasons. But yes, that delay happens in between each 1 degree increment. So there you go. That's a servo. Now I know I said we were going to be doing one with a potentiometer, but we're actually going to skip that in favor of working with transistors because I want to make sure that you guys spend some time with transistors. That's actually a pretty big part of electronics. It's kind of a big deal. I don't want to, I don't want to brag or anything, but transistors are kind of a big deal. So let's go ahead. I'm going to go back to circuits.io, and I'm going to open up the transistor presentation. Woo! So transistors and motors. This is different from servos. These are straight up just motors now. These will be motors that turn on and spin and spin and spin and spin, as opposed to a transistor, or excuse me, as opposed to a servo, which only spins a certain amount. But more importantly, we're going to spend some time learning about how a transistor works. And this is good because you'll have an idea of how your computer operates too on a circuitry level. Your computer is just simply made up of millions and 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 millions of transistors. Just tons and tons and tons of transistors, like the size of the thickness of your hair. Tiny, tiny, tiny transistors, and they're all laid out, like certainly on the CPU in like a three-dimensional thing. So there's like multiple, tiers of transistors, and they all communicate in a three-dimensional way, like up and down tiers and everything. It's pretty wicked what they've been able to do with transistors since their inception. So I think it's kind of interesting. Your mileage may vary, but I mean, if you're doing this, you might at least have a passing interest in how this kind of stuff works. So hopefully you'll agree. So a transistor is a semiconductor device used to amplify and switch electronic signals and electrical power. Well, that's kind of a confusing way to put it, but it elucidates on it in subsequent slides. So transistors are in a branch of components called semiconductors. A conductor is like a train conductor, allowing electrons to move. A semiconductor is like a part-time train conductor, only allowing electrons to move if they get paid. Cute. As you can see, I had a friend write this for me, and I've given him grief in the past about his spelling. So he had some choice words about that. But yeah, so transistors essentially only conduct electricity along a path given specific conditions. Essentially, semiconductors are always receiving electricity along the collector, but they're not always emitting electricity along the emitter. That's where the base comes in. The base, you can think of like a signal. If it receives, depending upon the type of transistor, if a transistor receives a signal along the base, it will then complete the circuit between the collector and the emitter, and thus allow the electricity to flow through it. Again, this depends on the transistor. Some transistors will complete the circuit between the collector and the emitter if it is receiving a signal. Some will complete the circuit between the collector and the emitter if it's not receiving a signal. And that's just, yeah, that's just different types of transistors. But anyway, yeah, the collector holds back a massive amount of potential electrical energy, or just simply electricity. And then the base controls when the electricity can go, basically go from the collector to the emitter and then continue along the circuit. If it gives it the green light, then the emitter will emit the electricity and let everything continue. So you can think of it like, and they have this example here, you can think of it like a dam or a floodgate. So when the base is turned on, the floodgates open and electricity is allowed to travel through. Water is allowed to travel through in the case of a floodgate. So it only allows electricity to move if there is a charge at the base. Again, in specific types of transistors. There are very few absolutes in electricity except that it will give you a headache. This is true. A headache. There we go. There are always exceptions to the rule and everything like that. In this specific case, there are certain transistors that will transmit when it's not receiving a signal. But anyway, that's pretty much the basics of a transistor. Now, the thing about it is you can link transistors together in specific configurations. So you can have a transistor hooked up to a circuit, and then let's say this is the emitter. The emitter could be hooked up to the base of another transistor. And then this could also be hooked up to, let's say this is like 5 volts of power. So when you're, when you got a base here, you're sending down electricity. Neither of these are transmitting. But if you send a signal through the base, this one turns on, which allows this one to turn on, thus allowing electricity to continue. You could flip these around, so this could be a transistor that only transmits when it's not receiving power. So electricity is always traveling through here unless you receive a signal in here, which turns this one on, allowing electricity to travel down this way, which turns this one off. Doesn't seem like much now, but by combining transistors, many, many, many transistors, you can have basically logic. You can have logic circuits and things like that, which are the foundation of computers. So now let's move on to diodes. A diode is a component with asymmetrical conductance. It has a low resistance in one direction and infinitely high resistance in the other. Essentially, it's like a one-way road for electricity. LED is short for light emitting diode, as I've said before, and that is why it matters which direction you plug an LED in, because the electricity will flow in one direction, but it will not in the other. So if you hook an LED up backwards, the electricity will not flow. The circuit will be broken, your LED will not light up, and everyone will be sad. A diode is the same way, except it just doesn't have a handy, indicator, and that it doesn't light up if you have it hooked up the correct way. A diode will simply just break your circuit if it's not hooked up the right way. So that's another thing to check out. If you have a circuit that has a diode in it and the circuit isn't working, check and make sure the diode is plugged in properly. As far as schematics are concerned, the arrow indicates which direction electricity should be flowing with a diode. So electricity should be flowing this way. If that diode was hooked up backwards, well, then electricity would not be flowing. Now, an LED in a schematic has pretty much the exact same symbol, except it has 2 arrows coming off of it. And those arrows are meant to symbolize light, and that just lets you know that it is a light-emitting diode as opposed to a regular diode. So with that quick little crash course in diodes and transistors, let's actually mess around with a transistor and a diode and a motor. We're actually going to bring all these 3 things together and the Arduino to make a motor turn when we feel like it. So let's go ahead and get that started. I'm going to create a new circuit like you do. And yeah, here we go. Here's a better diagram of how to hook it up. Now, it looks like there's a lot going on here. Kind of is, but don't sweat it. Sorry, I missed the mute button for the first couple of coughs. So I was trying to temper it. Anyway, as always, let's rotate our breadboard, and we'll bring in an Arduino Uno R3 to no one's surprise. Rotate the Arduino. Bam. Now, we're going to add, let's look up a motor. Let's see here. We got a DC motor. We've got a couple of different types of DC motors. Oh, whoa, hello. Okay, go away. We're just going to use a regular DC motor. And this is going to be a PMOS transistor. Well, actually, let's see what different types of transistors we have here. It's going to be a PNP transistor, not a PMOS. My mistake. It should be. It should be a PMOS or a PNP. All right. And then we're going to grab a diode, and we're going to grab a, what is this? This looks like a 330 ohm resistor. So we'll go ahead and grab the resistor right now. Bam. And we'll grab that diode as well. Bam. And those are our components. So we have one diode, one resistor, one transistor, and one motor. Let me go ahead and rotate the motor around and make the resistor 330 ohms. Bam. And let's get this hooked up. So we're going to have our common power and our ground, just like we always do, or we have been doing. Let's go ahead and get those plugged in. Wait. Helps if you actually hook the ground up to the common ground as opposed to the common power. Bam. And then we're going to hook up our power, the common power, and make sure to color these appropriately for readability. And we're gonna get this built. All right. So let's see here. We've got only one wire coming out of the Arduino, one signal wire, and that is pin 9. So let's go ahead and get started on this crazy journey. From that pin 9, we're going to be hooking up a lot of stuff. Okay, there we go. Make sure to give yourself enough vertical room in order to get this hooked up. Bring it around to A5. And I'm going to turn it a nice visible color. Let's make it pink. Very visible. So, pin 9 is going to be hooked up to our 330 ohm resistor. Let's go ahead and rotate that, and we'll put it on D5 and F5. So there you go. Now it's hooked up to the same rail, and it's jumping across the middle plastic bit to row 5, columns F through J. Then we're going to hook up our transistor on that as well, and the base is going to be hooked up to that rail. So you notice that we got the emitter going one way, the collector going the other way. The base is hooked up to the the resistor, because remember, the base is going to determine whether or not we're producing power. So by extension, this is backwards. Is it though? It's not. Odd. Oh, interesting. This is not at all backwards. Okay. So our collector, okay, the transistor is backwards. So our emitter, that's annoying. Our emitter is going to be hooked up to the common ground. Go ahead and bring this out. Bam. And we'll make it black, just so we know specifically that it is hooked up to the ground. Oh, no. Yes. And then our collector is going to be hooked up to our motor. So let's go ahead and throw that down there for now until we get our motor all hooked up. Now we're going to hook up our diode. So our diode, we're going to put into column I. I have it running from 15 to 19. And we're also going to hook up our transistor to row 19 as well. And we'll make this yellow. So you notice that our transistor is also hooked up to this diode. Now let's hook up our motor. So terminal 1, which is our ground, our output is going to be hooked up to 19 as well. We'll make it black. And terminal 2 is going to be hooked up to our common power, I believe. Ah, the other side of the transistor, or the diode. Oops. And then our diode is going to be hooked up to common power. All right. And with that, we should have everything hooked up. This looks a little confusing, but don't worry. So essentially what's going on here is the motor is always going to be receiving power from our common ground. As you can see, it's hooked up to the diode, to this circuit here, and it's hooked up to the motor. And the motor is going to be sending power out through the ground. And as you might notice, it can go, well, two different ways. Either it can travel up this and into the diode, or into the transistor, or it can travel up the diode and back into the motor. It cannot travel the other way. This diode only allows electricity to travel from the negative end of the motor back into the positive end. Now, this transistor will essentially be stopping the circuit up here. So it will always be traveling up the diode, back down into the motor, up the diode, back down to the motor, up the diode, blah, blah, blah. Unless we receive a signal from pin 9 on the Arduino, in which case the base is signaled, the connection opens, and so now the electricity can travel from the ground out of the motor, up through the diode, out through the common ground, into the ground in the Arduino, and thus the circuit is completed. Here we have no ground, so the motor should not run. Hopefully that makes sense. It's a bit strange compared to what we've done before. But essentially, the motor has a diode on it to make sure that it doesn't feed back into itself. And the circuit is completed once the transistor receives a signal to complete the circuit. So let's mess around with the output side. because it's one word. That's why it's freaking out. So, programming side of things. Void setup and void loop, like we always need. I'm going to go through this rather quickly because I want to make sure I get as much of this done as possible. We might actually just have the motor turn on and then off, as opposed to doing all of these different functions. So we're going to create an integer variable called motor pin, set it equal to 9, and we're going to say pin setup, motor pin, output. Just like we've done before, we're setting it up to be an output pin. And then we're going to say motor on, then off, blah, in our void loop. This is a little bit unusual. This is not something we've generally done before, but what we're doing here is we're calling a custom function. And this gets back into things a little bit. Void loop and void setup, these are what are called functions. You don't, technically. You can use it. I'm opting to skip that for the sake of, well, I was doing it for the sake of not having to explain it. But essentially, this creates a variable that we can modify, so we can change motor pin later on. If I stick this const in front of it, that's short for constant. That means that we can set this to be pin 9 when we create the variable. So constant integer motor pin equals 9. We've established that we've created an integer variable called motor pin. It's equal to 9. We've established all that. We've also established that it's a constant, which means that we cannot change the value of motor pin later on in the program. We cannot say motor pin plus plus or any nonsense like that. We can't say motor pin equals 15. Like, we cannot do that because it's a constant. We established it once here. It can never ever change ever again. That's something that's good practice to have, but it wasn't strictly necessary for this program just because we should not be writing anything that could accidentally change the motor pin value anyway. But life's full of strange things. Sometimes you run into situations in which you can accidentally change the value of motor pin. So you do a constant there, which just sort of is a self-check to make sure that you don't accidentally change it, because the compiler will be like, hey, yo, you shouldn't be changing this. You can't change this. Fix it, fix it, fix it, fix it. I don't know what that was. It was a re. Anyway. Yeah, for sure. No problem. So look at that. What I've done here is I've created another function with our own name, motor on then off. We've got void loop, we've got void setup, and now we've got void motor on then off. And this is just simply a function. A function is just a block of code that you can run your own, like you can run statements in. And the strength of a function is you can repeat it as many times as you need to. You can just call it. You can think of it like a loop, except a loop that you can call from any part of your program on command. Whereas with a normal loop, you have to invoke the for loop, and then you have to, say how many times you want it to run, and then you have to include like the math that, and then potentially it could run, a weird number of times or something like that. And even then, you will have to include all of the code that runs inside of the for loop, if you want it to run in a different part of the program. With a function, you can write all that code once. And then you can tell the compiler, you can tell the computer, you can tell the Arduino to run all of that code with one line, which is the name of the function. So that's what we're going to do here. We're going to say motor on then off, and we're going to have some pretty useful, we're going to have some code here. So we're going to say int on time equals 3000, int off time equals 3000. And again, you could have these be constant integers as well if you wanted to, because we're not really going to be messing around with them in the code. And we're going to say digital write motor pin high delay on time. Digital write motor pin low delay off time. And that's going to be our custom function. It's simply going to turn the motor on, it's going to wait for 3 seconds, it's going to turn the motor off, and it's going to wait for 3 seconds. But it's not turning the motor on and off directly. What it's doing is it's allowing the transistor to open and then close, which is completing and then breaking the circuit that the motor is on. So that's what we're doing here. We're telling the motor to turn on, wait 3 seconds, turn off, wait 3 seconds. Complete the circuit, wait 3 seconds, break the circuit, wait 3 seconds. And this is our entire motor on and off function. We could actually replace this right here with all of this code in here. And we'd be functionally doing the same thing. However, the power in this becomes, we've just told it to run again. We've actually put all of this code, like again, we can replace this right here with all of this code. We could do the same thing here. We could replace this here with all of this code. If this wasn't a looping function, like if this ran once, we could then call all of this code twice without having to repeat ourselves. Now again, we could do that with a for loop, but we can also call this function elsewhere in the code, and that's the power of it. If we wanted to loop it a couple of times in another part of the code, let's say we had a for loop here that did essentially this but multiple times. Let's say we wanted to do it in setup as well. We would have to include an additional for loop, and we would have to include all of this code to run inside of the for loop, even though we have it down here. So that's the power of custom functions. It allows us to repeat bits of code very quickly and very easily. So let's go ahead and copy paste all of this code into our Arduino simulation. And here, I'll go ahead and put it into the chat box as well so you guys can take a look at that code. Copy and paste, upload and run, and we should see, ooh, whoops. It's because it's not pin setup, it's setup pin. R. Wait, what? Oh, pin mode. Oy. Doesn't matter how many times you do this. Sometimes you'll forget. So we should see the motor turn on for 3 seconds, and then turn off for 3 seconds. And then turn on for 3 seconds, and then turn off for 3 seconds. And then just over and over and over again. And that's that. That's what we've done. We've made a motor turn on and off using a transistor and a diode and an Arduino. Woo! Yeah. But hey, so do you understand exactly what's happening here? We're actually not directly turning the motor on and off. We're turning the transistor on and off, which is completing the circuit, which is allowing the motor to turn on and off. But, whew, managed to just squeak under 9 o'clock for the transistors there. I know that was probably a little bit fast, so I'm going to, leave it open for question and answer time, obviously, so you guys can ask questions about what we just went over. If you understand it, though, then fantastic. That's awesome. But if not, I totally don't blame you. This was a little bit faster than usual. I wanted to make sure I got through the hardware and the software side of this in this class, because this is actually, like I said, the last one before you guys do your competition. So if you have any questions about that, if you have any questions about the competition, I'll answer them to the best of my ability. Otherwise, you're more than welcome to head out. you know, best of luck with everything. Just remember, approach everything with a critical mind and with the knowledge that you've been given, and you should do just fine. But yeah, best of luck.